It was a pleasant way to break up what I was having to do, because otherwise it's mindless marking of telling engineers, oh, differentiate this, and then they don't differentiate it. And you had one job. This for this.
Most of my problems these days.
Yeah. They're a joy to teach until you start reviewing material that they give you back and you go,
Yes.
oh, that nodding was empty, you see.
To be fair, I'm pretty sure I do the same still. You listen, oh yeah, I totally get that. Or I talk to you, before you go on vacation, like, yeah, I totally understand this, and then you're gone, and I'm like, oh.
Well, I mean, I'm pretty much the same as well. Like everything you said about all this here, just like, okay, that's slowly dissipating out of my mind. I didn't realize there was viscosity in this system, but okay.
Where are you based? It's
Seattle University.
oh, right.
It's like how I actually how I met Pat.
Yeah.
Undergrad research student.
Oh, right.
Yeah.
Oh, was he? So, I don't know, what's his connection to Seattle University?
He did his undergrad.
I should have known.
Oh,
Yeah, everything seems to be.
Easiest job of the
Thank you
day.
very much.
Was already sent. You just put the PDF file. Quick PDF. Okay, that's it. Right. Still got 2 minutes. Yes, about 3:30. That's what happened.
We'd have solved it by now if we had those extra 2 girls. Ways to move away from using beamer for those presentations. And I know Miles gave me.
I was gonna say Miles is.
He's extremely passionate. He's
Yes.
like, look, if you're still using beamer, you are a thief. Yeah, there's this one that essentially works. I forget its name, and I had it bookmarked. But it allows you to do like asymptote just more intuitively do kits, like without having to code it. Say line here, and it goes, okay, here you go.
Yeah. What did you even use paper?
Sometimes I do, but then I like
Yeah. I've recently done what's likely a fun circle I've been using Keynote and yeah. It's like, yes, I can move it around. Like, actually, that video necessarily work. I don't need to download them. Oh yeah, it puts a tax on like, okay, if I'm a system, yeah, it's like, okay, it will take me an extra 10 minutes to make this for you. So here you go, I guess this is not.
I think we can start. 1 minute in. So, okay, hello everyone. Welcome to this session today. So, so it's a big pleasure for me to introduce Boris Konopelchenko. So many of you already know him. So Boris is emeritus professor at the University of Salento in Lecce, in Italy. So where he came 29 years ago after being a professor at Novosibirsk State University, and so then he joined the University of Salento as a distinguished professor. So Boris wrote 2 monographies on the subject of nonlinear integrable systems and multi-dimensional nonlinear integrable systems. He gave important contributions in many areas, from the method debug and method for multi-dimensional systems to the introduction of new concepts like the theory of the generalized Weierstrass formula, which are connected to deformations of 4D surfaces in integrable systems. So many other contributions in the theory of the application of dispersionless systems, and there are many things, also connections with ancient mathematics, the Menelaus theory, and he discovered the Menelaus theorem in the context of integrable systems. So lots of contributions across a wide range. His approach to science is encyclopedic. So I will stop now, and I'll let you enjoy the talk on multi-dimensional Jordan chain and Navier Stokes equation. So the stage is yours.
Thank you, Antonio. Thank you very much. You were too kind, in fact. I did much less. Nevertheless, I had an interest always in integrable systems. And I try my best to present something connected with dispersive hydrodynamics and during this program. But if you will take a look on the title, immediately we have some doubts. Nevertheless, I am very grateful to all organizers, Antonio, and also other organizers of the program for kind invitation, possibility to participate in this program, possibility to turn back to Cambridge, to this institute. It's really a great pleasure to be here, to meet old friends, to revive old collaboration with the hope to start a new one. Okay, thank you very much. Okay, the title of my talk is written there. So it's multi-dimensional Jordan chain and Navier Stokes equation. In details of what I will say in the second part of the talk, you can find this recent paper. Navier Stokes equation is the following equation in the rather simple form, where I probably shouldn't explain notation. U is a velocity vector, rho is density, P is pressure. This is just Laplacian. Nu and eta are 2 coefficients of viscosity, usually called it first and second viscosity. And this is one of the simple form. Of course, very much more complicated, external force, all of that. Okay. And Navier Stokes equation apparently looks pretty simple.
Probably a naive question. What are the effects of the second viscosity? So the first one is just energy dissipation. The effects of the second viscosity, what dynamically is that doing?
I mean, connected with this constant. And usually, if you take all classical textbook, Landau ratios, LAM, it's connected with the fact that construction of the stress tensor.
Mm-hmm.
In stress tensor, you should select, divide 2 paths, with stress equal to 0, without stress. Okay, this somehow may look strange, artificial, but not artificial if you begin to discuss some application of physical meaning. I will not do this. I will not touch Navier Stokes equation itself. It's too serious problem for me. Instead, I will try just today to discuss one possible approach which can lead to Navier Stokes equation, in probably one strange but surely non-orthodox or non-standard way. And the main personage which we will meet on this way will be exactly Jordan chain, which was mentioned in my title. I will explain it all later. Of course, Navier Stokes equation, there are many thousands of papers, research devoted to Navier Stokes equation. It's a difficult problem, you know, much better than me. And of course, the most of them research are connected with different various approximations and different simplifications. And the most simplified case, which you know perfectly well, is one-dimensional case when you can drop out all things which appear on the right-hand side. Forget all physical effects, forget nothing. You end up with a simple equation which has different names, Riemann, Hopf, Burgers-Hopf, and so on. And this is the textbook example of application of various methods, how to solve, how to find, how to describe the waves, nonlinear waves, because you have here U here. And of course, it's very easy. Okay, so different ways. One of them is just to use holograph equation. This is all textbook. Write down this equation with some function f of u, fixed function f, try to solve it with respect to x in t. Then one can show it's in all textbooks. This u will be solution of this equation. Everything depends on the choice of the function. This function f is in fact, one can easily see locally inverse to initial data, locally inverse, but t equals 0. So for different initial data, we will get different solutions with different behavior. One important phenomenon which usually associated with the study of this equation is so-called gradient catastrophe. No, I didn't present it here, but so no one's nothing to. If you have a wave profile, they begin to propagate, then at some point it begins to break. So at some point, derivatives of u with respect to x become infinite. Okay, no. I wouldn't pretend to face something reasonable new. I'm sorry at that point. Everything, all that can be described with the use of this holograph equation. There is some line curve along which it happened first time and so on. One can calculate behavior at the point of the gradient catastrophe at the first time, gradient catastrophe, and so on and so forth. All known. And this is in fact a prototype example for other studies. Okay, of course, first extension will be to pass to n-component system, written in more or less same form. It's not always can be done, but when it can be done, the system assumes the following form of the n equations when sort of diagonal. Diagonal sense, we have this for each I, we have the only one function. I are so-called Riemann invariants, lambda are characteristic speeds, and it was shown back to Gauss, or probably even earlier, I am not expert. Okay, some equation of the hydrodynamics in one-dimensional flow can be reduced in this form with some specific characteristic speed. Of course, there was a middle equation. Okay, in one dimension, previous case, one Burgers-Hopf, it was clear how to apply, for instance, holograph method, how to proceed in this case. And strangely, or miraculously, it was done only by Sergei Tsarev in 1985, long time after all this story began. It was shown that, in fact, I will not present it here, it's also very well known, sort of extension of the previous formulas, these formulas, but for n components, not trivial, in fact, which allow to construct solution of the system of equations in terms of Riemann invariance. And there are a number of properties associated. It was shown there is some very beautiful geometric structure behind Riemann spaces with so-called Yegorov metric. There are meaning of all coefficients which appear. Christoffel Silver's all the story, very rich story. In particular, it has been shown also that for this type of systems there exists very nice Hamiltonian structure in the works of Dubrovin, Novikov, and many others. So this type of system has been investigated very intensively in great details. But it was not always possible. In fact, not that easy. There are a number of conditions which should be satisfied. In the first, but it was rather simple in the sense because we have here just functions. What will happen if we put here instead of lambda some matrices, not that simple, not that trivial, but some possible effect has been done by Yuji Kadamov here a long time ago also. One can extend holograph method to the matrix case, but with some not so obvious, not so simple in a sense as the Zarov method. Okay, this also to say that in one-dimensional case there are a lot of results. But of course, one-dimensional case is not that realistic. In real life, we have at least two space dimensional vector 3. How to extend all that to high dimensions? That was always very good question. For instance, how to extend the result from this type of system to the following system with any dependent variable xi, xk, and with some functions or matrices here, it was not clear for a long time in general case. The Hamiltonian structure of this type of equation with some particular choice of has been analyzed in papers of these authors. There are very nice Hamiltonian structure with specific properties done. But as far as concerning Hatovov method, there was no result to the best of my knowledge. And they were invented different methods to try to solve, to show integrability of the system of multidimensional system at that time. One of the methods was so-called hydrodynamic reductions invented by Ferapontov and Nusnudinova so many years ago. And many equations have been investigated, analyzed from that type of approach. Okay. This is about what I thought about the dynamical type system. There is another sub-objects which appear during the study of dynamic type systems, so-called dynamic type chain. Chain would mean the system of equations with infinite number of dependent variables. First example has been produced by Benny in his study of Benny equation of long base, one-dimensional case. Instead of writing the system of equation in terms of two dependent variables, let's introduce so-called momentum of them. Then he showed that Benny equation can be converted, equated into the following infinite chain. K run from 0 to infinity. Okay, one can say, what's the advantage of that? In fact, there are many of them. This type of approach then has been extended to other cases by Kupferschmidt, Albert, and Mikhailov in different ways. I will mention among of them, mention only one, which is a chain produced by Martinez, Alonso, and Shabbat 20 years ago. And they are studying all the dispersion limit of the integral equation associated with the Schrödinger operator with the polynomial, which depends polynomially on energy. They discovered the hierarchy of a dynamical system, chains, with very specific interesting properties. I present here just first member, first time. It's the following chain of equation where n run from 1 to infinity, I will call the MAS chain. Similar chain somehow has been introduced by Maxim Pavlov in 2003, long time ago, in connection with the study of so-called epsilon systems, 1 + 1 epsilon dimensional system. This system, in terms of Riemann invariance, a very specific form of Riemann invariance. After introducing these moments of the Riemann invariance Im, where m run from 1 to n, he showed that epsilon system can be converted in the following chain. Again, 1 + 1 dimensional chain, where I see k are variables. I would like to stress that not all of them are independent, because they are of the following form. There are only m function independent among them. Nevertheless, there was such a chain. All of them has been introduced somehow considering dispersion's limit or quasi-classical limit or no integral hierarchies.
Sorry, Boris, just a notation. In the previous equation, Martinez Alonso Shabbat, so it's a derivative with respect to t of yn equal to y1.
No, yn.
No,
y1.
Is it y1?
Y1, yeah. It has a rather specific form. And due to that, it has nice property. I will not present the properties, I will discuss some of them later. Okay, this type of chain appeared also in quite different subjects, better to say completely different subject. In our study with Yuji Kadama of so-called confluence of happy geometric functions and the connection to the integral dynamic type systems. Okay, this is just classical subject. Take Gauss happy geometric function. If you do follow some certain process of degeneration, you will end up with an airy function. It's classical old books. And then it was shown that behind that, there is one can associate with them some particular hydrodynamic type systems associated with so-called Laurentieri type functions, plus minus all that. I will not repeat all the discussions. But in the most degenerate case associated with airy functions, for shown that one can system associated which describe dynamics of the critical points of some functions are governed by some very specific equations. In the most simplest case is the following system of two equations. Again, one time, one x. But the matrix here is rather special, as you can see. It's not diagonalizing. The Jordan block with the eigenvalue U1. All previous systems I showed, I mentioned before, most cases studied cases when you can diagonalize system. You can introduce Riemann invariance and then characteristics. For this simple system, no way. Jordan block is not diagonalizing. But nevertheless, it was shown that system is integrable exact. In the same sense, you can write down Hadrograph equation, find solution of Z. Infinite hierarchy associated with this system of two equations. Then, in case of arbitrary n, the corresponding system is presented here. Again, you have a Jordan block, the most degenerated Jordan block with a single eigenvalue U1 and 1 above, and all others are 0. Again, the system is integral. In a sense, you can construct solution by Hadrograph method, and there is hierarchy of equation of laws which commute with this system. In fact, it somehow was the first indication of the existence of the system of the non-diagonalizable time. I would like also to stress it's exactly the case of so-called parabolic system. When you have full complete degeneration of eigenvalues, it has a parabolic character. Before, system discussed before were all strictly hyperbolic or elliptic. In parabolic case was not studied well before. And this was these systems were of the type were examples of the parabolic integral systems. Okay, if one formally extend n to infinity formally, one end up with the following chain of equations. So this matrix will be infinite dimension. Following chain of equations, for us it looks completely new, very compact, but then it was shown that, okay, in fact, it's connected with the previous chains, Martinez, Alonso, Shabat, and Pavlov, when I mentioned before. And in fact, relation between this chain, we call the Jordan chain, with the MAS change is very simple. This is that change of variables from U to Y. Given, oh, this should be Y, I'm sorry, not P. In this formula, P is just elementary Schur polynomials. So, okay, it's written here. So, if we will start with the Jordan chain and pass from the function U1, U2 to Schur polynomials and call it Y, we will get MAS chain. So they are just equivalent. The same chain written, just at different variables, no more, no less. Similar things happen for Pavlov case, and this is a identification even much more simple. But I would like to say that in our case, all these variables are functionally independent. In contrast to Pavlov's case, where only M functionally dependent variables. Okay, nice chain, very beautiful, and so what you can say, just a toy, just to get. Is not, okay, in fact, Jordan chain, or you can say, I call it Jordan chain, but of course it just, as I said, this is Martinez also Shabbat chain, or call it as you like. For simplicity, I will call it Jordan chain. Just to emphasize, because we have a Jordan matrix here. Infinite dimensional case to say that we have the Jordan matrix, little bit too much, but nevertheless. And I would like to show this Jordan chain, in fact, is something more serious, a simple toy chain, by the following reason. It was observed later, Giovanni tells us, the Jordan chain appear or may play a role as a regularizer of the gradient catastrophe for Birkhoff equation. Okay. This is just Burger's Hop equation. I wrote the second slide. As I said, it has solution described by the Khodolov method, and it has a gradient catastrophe phenomenon. At a certain time, derivatives of u respect to x and y becomes infinite. How to regularize them? Old question, okay. But I will try to go a little bit back just to stress what usually means regularization, how it proceeds. In all cases, we know regularization is achieved when some new degrees of freedom enter into the game, one or another way. Which way is a good question? Okay, so we will first our rule for regularization. Second rule, okay, this is equation without no effect of physical effects of dissipation, viscosity, dispersion, and so on and so forth. But in physics, it's just sort of axiom that first effect which enters the game, if some derivatives become very large, effect is this dissipation, one or another form. Do you like it? Do you dislike it? In physics, it works like that. Or friction between the layers, or viscosity takes the form of viscosity, there are dissipative effects. Dissipative effects, as we know very well, are described as by parabolic equations. Nothing to. So the second point in our procedure of regularization will be the equation which will try, in which we like to write to regularize gradient catastrophe of Burger's Hop should have parabolic properties, should be parabolic. And then, okay, another third property, not that important. In all effects described in hydrodynamics, of course, you have propagational waves, but in most cases, when we consider the usual motions, entropy just moved with the fluids. This means that long derivatives of entropy is always zero. In other words, entropy always obeys the transport equation associated with the corresponding equation, even with this equation. Okay, and combine all these three rules, one can show that, okay, let's extend our one equation to the system of two, adding one new degrees of freedom. Let's call it U2. What is degree of freedom is a good question. Okay, let's count it function the degrees of freedom. U1 is 1 degree of freedom, U2 function of x, another degree of freedom, so on and so forth. From that point of view, derivative of function add immediately infinite number of degrees of freedom. We would like to add only one, smallest, minimum possibility. That's one. And we end up with the following system of equations. It is exactly two-component Jordan system. Sorry, I presented before. Moreover, okay, very nice. But now we should check what happens with all that. And one can show analyzing this all from the point of Khodolov equation, or doing just double scaling expansion around the critical points for the Burger's Hop. One can show that an extension of this equation, Burger's Hop, to two-component Jordan system, first level gradient catastrophe disappear. It does not show up here. How it happens like that? Well, because we add new degree, an additional degree of freedom, something should change. And first order gradient catastrophe with the behavior epsilon minus half of the derivatives disappear. Unfortunately, not the end of the story, because for that equation, we have second order gradient catastrophe, which happens at the first time, epsilon minus to a third. No, it doesn't disappear, but if we extend our equation to a Jordan chain, it becomes the first order gradient catastrophe for Jordan system. But now we know how to proceed. Just to kill, say so, this first order gradient of here, let's add one more degree of freedom, U3, following our rule. So this means that here we will have a Jordan block to describe, to be presented the parabolic character of the system. And one can show, passing from this two-component to three-component system, first order gradient catastrophe disappear passing here. But second order gradients remain. Okay, and then one can continue this process. Okay, and standard question, of course, we should distinguish between the two cases discussing behavior function. So-called generic case, we have generic function, or I will call it, I have here so-called Poincaré case. Poincaré case, difference between them has been formulated by Poincaré in 1870 something, I forgot the recitation. Translation is something like that. If you would like to understand better the phenomena which happen in his discussion of the behavior of the particles for dynamical system, you should consider not only one solution, even generic one, but the large family of phenomena which are close to that. Only this way you will understand better and deep what is going on. This means a simple thing, for instance, for Birgershoff equation. Of course, you can say, let's consider generic initial data. So a generic function f. There are only two possibilities to put. Two-level gradient catastrophe may happen. Connected with the fact that for function of one variable, you can impose only one constraint, one condition. No way. But if the function depends on a certain number of parameters, you can proceed. We will change parameters. You will always have points where it happened. Okay, so this means if you were doing this way, speaking about infinite family of initial data, you have infinite number of gradient catastrophe discussed with you 20 years ago. You will need to regularize all of them. So you will need to go to n-component Jordan system when n goes to infinity. So you end up with the Jordan chain. And in fact, we showed in this paper, in this process of regularization, an extension or embedding, say as you like, of Birgershoff equation into the Jordan chain, all gradient catastrophe will be regularized.
I've got a quick question, a little confused. So in the n=2 case, and indeed in all the other cases, if the j greater than 1 variables are 0, that's the solution.
Sorry?
So in the n=2 case, the second equation always has the solution u2 = 0, and then you recover the Burgers equation. So isn't there a singularity?
Of course, if you restrict your two-dimensional space to the to line, you go to 0.
Right.
Yes, of course, you have all which happens with Burgers equation. Idea is exactly the extension, because U2 is interacted. Second degree of freedom is connected with the first degree of freedom. Due to this interaction, say so, in physical terms,
Okay.
This effect disappear.
But is there something like a positivity?
Sorry?
Is positivity invariant for that second equation? So if U2 stays positive, it begins.
No, of course, it's subclass of solution. For this subclass of solution, you turn back to Birgershoff.
Yeah.
No, you really turn back to Birgershoff. But the idea is just, or you go in one direction, if you extend to the plane, okay, and there is, if you remain on this direction, one direction, okay, everything remains as it was before.
Yeah.
No U2. The idea is just to have another degree of U2, another coordinate. And possibility to go out, just destroy the gradient catastrophe. So in physics, it's standard effect you see. For instance, propagation along one line, if you have two-dimensional, there are some effects in orthogonal direction which completely, not completely, many times change behavior. Diffraction, no, physics, there are effects just which are doing something like that. Interaction with another degree of freedom, or integration with the original degree of freedom with another one. In a way, some effects will disappear, will not repeat.
Degree of singularity change.
Sorry?
Degree of singularity change.
Degree of
Singular, singular structure change from one to the next.
yeah. In fact, no, one can do it in one way. Okay, one can do in Kadogorov method. There is some method that should be equal to 0. It happens on certain line. If you pass to this one, this condition where for Birgershoff derivatives blow up means nothing for that. There is another condition for U1, U2 to blow up. Or you simply do just expansion and double scaling expansion, which is okay, should be done properly. Well, okay, Okay, there are several observations about that. In fact, all the procedure of regularization can be seen if it's shown in paper. It's sort of averaging process with generalized area distribution. Start with one dimension and with for some function which generate Birkhoff equation, and do an averaging with multi-dimensional area distribution. And you will see all these effects that simply disappear. Okay. Of course, very nice, very good property, but looks as again a sort of exercise, very nice. But immediately we will ask the question, but we know very well where to. Oh, I'm so very slow, I'm sorry. Very well the method to regularize the gradient catastrophe. For instance, to add the second order derivative to that equation, okay? Go to Birkhoff equation or to KdV equation if you like. Is there any connection with this type of regularization I just mentioned with the Jordan chain? Seems not. In fact, there is. Okay, let's write down Jordan chain. This is the first equation, second equation, so on and so forth. Now, let's consider the following constraint for the function. Let's put u2 equals the 1/2 u1 squared plus mu. Mu is a constant. Derivative of u with respect to 1. Okay, first equation is easily see. Turn to the Birkhoff equation, or you can ask what happened with other equations. Very easy to check. We see if you know u1, u2, where u1 obeys this, one can calculate u3 using this equation, and the answer presented is here. It's a differential polynomial. Everything in terms of u1. The same can be done for u4, for all others u. So with this constraint, first equation of Jordan chain becomes Birkhoff equation. Other equation serves as an equation to define recurrently all higher components of the Jordan chain. So it doesn't produce no constraint. Okay, this fact has been observed a little bit different way by Martin Salento about 20 years ago. Moreover, one can demonstrate. I presented there only the first equation of Jordan chains. There is whole hierarchy infinite number of times which commutes. What happens with hierarchy? One can demonstrate the whole Jordan chain hierarchy is reduced to the Birkhoff or Birkhoff hierarchy. Indeed, there is simple relation. Okay, for u1 derivative with respect to 10tk can be written in such a form, where Pn are elementary Schur polynomials already said. And one can show that under this constraint I mentioned, I haven't showed before, Schur polynomials assume the following form, everything in terms of u1. And this equation consequently become the following infinite hierarchy, should be equal to 0, sorry. Okay, equal to 0.
Sorry, Boris, when you said u2 equal to that expression,
Sorry?
when you said u2 equal to that expression, and you substitute into the second equation, you get everything vanishes?
No. I will get expression for u3 in terms of u1. That one.
So you were working on the,
So,
the infinite
okay,
chain.
I assume that u2 is that one. Substitute here, I have the following expression for u1, okay? u2 is expressed in terms of u1 in the following form.
Okay,
Now, the derivative of u3 with respect to x equal minus u2t minus u1 du2 with respect to x. So u2 is here. I should calculate derivative, and then I should use this equation.
Yeah, okay, so you need the
And the
function.
answer will be, and it can be integrated, in fact. This is sort of miracle we're discussing now. Not always happen. U3 is written here. Then you do the same with the next equation, you get expression for u4 and so on and so forth. So what is remaining is just Birkhoff equation. So, well, okay, and this equation, okay, I said equal to 0. This is no more, no less as well-known Birkhoff hierarchy. And this operator is well-known recursion operator for Birkhoff hierarchy. So what does it say us? Solutions of the Jordan chain under this constraint becomes a solution of the Burger's equation and Burger's hierarchy. Vice versa, any solution of the Burger's equation is a solution of Jordan chain. Okay, indeed, take U1 as a solution of Burger's. Define U2 by this formula. You see by this one, so it's more or less obvious, all this will obey Jordan chain. So class of solution for Burger's equation is a subclass of solution of Jordan chain. Okay, all done with the Burger's equation now. Okay, the next question about KdV. Same story with KdV, not completely same, but very similar. Okay, let's impose the following constraint of our Jordan chain. Second derivative. First equation becomes KdV equation. Again, it has been mentioned, noted by Martin Shabbat, a little bit different way later. And we see, in fact, again, U2, U3, and so forth becomes all the differential polynomials under these constraints. Again, sort of miracle. Okay, there is some property of a sure polynomial behind that, something like that. Under this constraint I mentioned, sure polynomial pk becomes I in power k acting on 1, where I is the following operator. You can easily recognize the relocation operator of the KdV hierarchy. So this system of equation becomes the following system of equation is just KdV hierarchy. Okay, there are other properties, for instance, the formulas which appear just closely connected with the equation for resolving for KdV hierarchy started long time ago, McLean and so on and so forth. Again, all this show that KdV equation, KdV hierarchy is a sort of a differential reduction of the Jordan chain. And the class of solution of Jordan chain subclass is a class are solutions of a KdV equation hierarchy. Vice versa, all solutions of KdV equation are solutions of Jordan chain. Okay, one can proceed. In fact, this is a very good question, not quite clear. This took only two cases when everything reduced to differential polynomials. What are the particular properties? It's open question. Anyway, okay, all the story. I should go much faster. Sorry. We have no limit on time. In 1+1 dimensions. Of course, it's a good question. Okay, is there some? You see, you have a Jordan chain which can have has a simple and nice property. It contains Burger's equation hierarchy, KdV, OZ, and so there's regularization. Is there something like that in this 2, 3, or n-dimensional case? And the answer is, partial answer is yes. And this will be the second part of my talk, connected with this most recent paper about the multidimensional Jordan chain and Navier Stokes equation. Let's start with the construction of multidimensional Jordan systems, which I mentioned before in one-dimensional case. And this is the answer. Okay, this is just n-component Jordan system in one-dimensional case. And this is one possible extension of n dimension equal to n, where n is arbitrary. We have small n, capital N number of components, and small n dimension of the space. Looks okay. You can recognize here easily this operator, very nice. The rest is not that simple, but it has a simple meaning. Okay. Let's compare all the for n equal 1 component case here. In fact, starting equation Burger's equation, 2 components, 3 components, and so on. In this case, n equal 1 corresponds to the following system of equations, just homogeneous of the equation. This means take Navier Stokes equation or Euler equation, throw out all effects which appear, which contribute to the left-hand side. Looks simple, but not that simple, not completely trivial. At least it's n-dimensional. Okay, so behind this Jordan n-component Jordan systems, homogeneous of the equation dimension n. Okay, as I also mentioned, for n-component Jordan system in one-dimensional case, corresponding photographic equation receives the following form. This one dome. For this system, Jordan system, and n dimension, the corresponding Hanover equation are the following form. So you have n equation of that form and another capital N small n minus n equation of different form. Okay. If you take a look on this, you can easily see that function fi are locally indexed to initial data in n-dimensional locally indexed, of course. Other function has no simple mean. In the case n equal 1, only first system of an equation is presented. There are Hadograph equations for the homogeneous order equation. And this fact, in fact, has been known for a long time. And there are three authors which discovered that in different manner, as Ildovich, Chefran, and Fairley in these years, in different way. One is using Lagrangian coordinates, other is using Euler coordinates. Nevertheless, all of them are equivalent. All of them provide us with a solution of the homogeneous order equation in every three dimensions. In fact, it's not bad news, even very good news. Here in one dimension, we have this equation, of course, and also in n dimension, which is very nature extension, and not just extension which has definitely physical meaning. You see, this means this solutions are transported with the fluid. Total derivative with respect to t is equal to 0. Equation of the characteristic and so on and so forth. And they are governed by the following Hadograph equation. Any solution of the system equation for n equal 1 provided with solution homogeneous order equation in any dimension n. It has been shown by these sources. Okay, this is our starting how to get it. Okay. Let's start with the Hadograph equation which was presented in the previous slide, this one. Okay. Now, how to proceed? Standard way. Let's differentiate this equation with respect to xk and t. What we will get? This system of equation and z1, or it can be rewritten in the following form with the matrix A of that type, where matrix omega is a very special matrix, which have one identity matrix of pseudo n is the left-right angle, and all others are zeros. Okay, this we have the following expression. If we will differentiate with respect to t, we end up with the following relations, where v is the following line with n, capital N, small n components. Now, if determinant of matrix A, which is large one, is different from 0, we can invert it. We will have the following expression for derivatives. And now it's easy to see if I multiply this relation by uk, if I do a sum with respect to k, they will end up with the following system of equation, where you have still have matrix A, which is done of the derivative functions, our functions with respect to u. Okay, now let's impose the following constraint of this matrix. And one can easily see the system equation still to the n-component Jordan system, which was presented here. Of course, we have this type of constraint. What they mean? Okay, they mean something, some constraint on the matrix A, on the function f which are involved. Okay, due to this property, one can realize this constraint in the following form. Number of constraints here are exactly equal to number of functions involved. So it's not all the Devian system. If you succeed to solve it, okay, it's not completely simple because matrix A is done with derivatives of functions. So we have the combination of first order derivatives, nonlinear combinations, not easy to solve in general case. But anyway, any solution of the system, any set of functions f which obey this constraint, provide us with a solution of our n-component Jordan system in dimension small n. Okay, this Hadograph equation can be written in a different way and have some number of properties I will not have to discuss. But just to show what type of system we have here. Okay, this was for n equal 1, dimension equal 1, this was a Jordan system with 2 components. And this is just Jordan system in 2 dimensions, x1, x2, with 2 components. There are 2 eigenvalues. For n equals 3, dimension 3, the corresponding system with 3 independent variables, we will have the following form. Again, U1, U2, U3, but you see, 1 and 1 appears here in not complete regular way, but quite different from the naive possible extension to the dimensions. And I would like to stress these metrics, which are all particular choice of the Jordan blocks. That matrix is actually commute. All these matrices commute between themselves, and all of them are not diagonalizable. So this is just example of the systems in 2 and 3 dimension, high dimension of a parabolic type with non-diagonalizable matrices. And such that all matrices here commute between themselves. It's valid also for every dimension n. Okay, now what is the meaning of this Jordan chain? Again, as a one-dimensional case, it can be used for regularization of the gradient catastrophe of the associated with the homogeneous Euler equation. Or study of gradient catastrophe of homogeneous Euler equation in dimension n show that properties of gradient catastrophe or blow-up is quite different or very different from the one-dimensional case. Okay, using again differentiated respect to x, one end up with the following formula, and one can show, because we have n minus 1 where n is the matrix of constructed following way, that for homogeneous Euler equation, blow-ups happen on the hypersurface defined by the following equation, determinant of n equal to 0. M is a matrix n by n which contains t. So this equation is polynomial equation with respect to t of the order n. This imposes several constraints of the possibility to have or not to have gradient catastrophe, because in all this construction we are interested in only in the real solutions, real time, real coordinate, real function. So okay, I forgot to say everything I wrote before was a real value. So as for this, you immediately can see problem. In two-dimensional case, we have matrix 2 by 2. So the determinant of this matrix will be polynomial of the order 2 with respect to t. And you know, there could be situation when this quadratic equation with respect to t has no real solution. Because it would mean that in 2 dimensions, for the homogeneous Euler equation in 2 dimensions, there are initial data which are free of blocks. In contrast, for instance, for 3-dimensional case, you have 3-dimensional a cubic equation, and for cubic equation, there is at least, always exists at least one real solution. And so even on the dimension will have different group, and so on and so forth. Okay, in study of that has been some properties have been observed because in this paper, there are a number of interesting properties. In fact, one can show it is just working there, just to be completed, and probably will be presented in the larger workshop in 2 weeks, that one can show that for n-dimensional homogeneous Euler equation, there are n levels in generic case, in case of generic initial data, and levels of gradient catastrophes. Is the most singular behavior of the derivatives in n dimensions are given here. Epsilon in this power, where epsilon is go to 0. In 1-dimensional case, it would be 2/3. So in 3-dimensional, 3/4, and so on and so forth. Okay, there are a number of hypotheses I will skip. But now let's what happens if we will now again extend our homogeneous Euler equation to 2-component Jordan system. Okay, for 2-component Jordan system, we have the following matrix, and our previous matrix, which I called M, is just here in this corner. Remember the conditions as the derivatives blow up. What was the determinant of this matrix equal to 0? But derivatives, all derivatives for 2-component Jordan system will blow up when the whole determinant of the whole matrix will be equal to 0. Independent, if determinant of that equal to 0, nothing happens. All derivatives remain finite, bounded. In the case of 2-component Jordan system, and so on and so forth. One can show that in this procedure again, go into increasing n, you will keep one after another catastrophe of different orders for initial homogeneous Euler equation. If you do it for all, it's not, in fact, rigorously demonstrated. You should go to limit n go to infinity. So this means you could go to Jordan chain presented here. This is just n-dimensional Jordan chain. I run from 1 to n, any dimension of the space. Index I run from 0 to infinity. So it's infinite chain of equations, which again can be viewed as a regularizer of gradient catastrophes for homogeneous solid equation, with all particularities of n-dimensional case. It depends on dimension n. And now, since I have a few time now, we will write the Navier Stokes equation. Well, as we already saw in one-dimensional case, if I will impose certain constraints, I will end up in certain differential equation, Boris equation, KdV, and so on and so forth. Let's do something like that in n dimensions. It can be done in fact. Okay, take our n-dimensional Jordan chain and let's impose the following constraint. Now, what is rho is the function which obeys the following equations, continuity equation. P is the function, at the epsilon are parameters. Okay, I have changed. This is just Laplacian. I have changed, in fact, in n-dimensional case, there should be not 1 over 3, but another factor. Okay, doesn't matter. To simplify notation, there are 2 parameters, arbitrary parameters, because these coefficients you see obviously have a different behavior. Let's impose the following constraint. What happens with our Jordan chain? First equation, you can easily see, becomes the following system equation. And it is just an n-dimensional Navier Stokes equation. What about the other equations? Okay, let's write in the following form. So for increasing coefficient here. Okay, if we have L equal 1, okay, it was defined previously here. Now, and we know the UI obeys and Navier Stokes equation, we can reconstruct from it when u 2n plus I here. Would be the differential polynomial? It's a good question. I don't know. Nevertheless, in this procedure, you can reconstruct all higher elements of the Jordan chain, and there is no constraint on it. So under this constraint I presented before, here, Jordan chain is reduced to the Navier Stokes equation, and in n dimension. Of course, unfortunately, constraint on the matrix A becomes not that beautiful, not to say even something worse. Okay, but nothing to. But anyway, any solution of the system provides us via Khodorkov's equation solution of the Navier Stokes equation. The last question. Is it really helpful or effective? Very good question, we have no answer. What will be sort of miracle? Then, if you will succeed to do this, you will get all recognition in all possible senses. I don't know. But anyway, take any solution of Navier Stokes equation, any solution that is provided us with a solution, n-dimensional Jordan chain. So this means Jordan class of solution of Jordan chain, which is very large, contains as a subclass solutions of the Navier Stokes equation. What does it mean? How it can be used? Again, it's a good question. Now, okay, now we can consider some simplification. If you put eta here and epsilon equal to 0, we end up with earlier equation on the pressure. It's again the same story. And in fact, this constraint becomes much simpler. In fact, there is no resistance. Constraints of matrix A for function becomes rather simple in the case of earlier equation. Much better than Navier Stokes. Now let's consider reduction to the incompressible inviscid fluid. So rho is a constant. Of course, divergence of U should be equal to 0. This immediately assumes that classically for the following relation pressure intensity, and the constraint should be of the following form. And the equation which will have will be the following. Constraint of A are given here, not the simple part. Now let's impose another type of constraint, assuming that un plus I derivative with respect to I is proportional to Laplacian epsilon I with some coefficient. The first equation of Jordan chains become n-dimensional Boris equation which is known for the normal application. Turbulence also, if shall refer to one paper in physical course. Normal application. It's again a differential reduction of the Jordan n-dimensional Jordan chain with the following constraints of the matrix A. Okay, but there are other type of reduction in quantum space. You can continue. You can get any equation you like. Okay. But there is no constraint of the following type. So for parameterization of all our functions in terms of finite number of variables VIA, given that where epsilon are arbitrary constants. And one can show that the Jordan chain is reduced to the following set of n-dimensional equations, which looks like very similar to these systems in terms of Riemann and Boris, but not, because these lambda are not completely diagonal. But nevertheless, it looks very similar to what we had before. Anyway, it can be viewed as n-dimensional generalization of one-dimensional epsilon systems considered by Pavel, I mentioned before. As there is a chance, probably this type system is solvable. If we will be able to solve, then we will be able to construct solutions of the Jordan chain and consequently of the Navier Stokes equation. Okay, of course, it's very good question. Okay, very nice connection, but is it effective in any sense? Very good question. I have no answer at the moment. In some particular case, it may help. I don't know. Very good question. Okay, and in last, I have probably for 5 minutes. Being here in the program, dispersive hydrodynamics should be something should be mentioned in connection with dispersions or effects of that type. Before we obtain equations, Navier Stokes, other equations which describe effect of dissipation, viscosity, and other. No dispersion at all. Of course, we know from physical point of view, the dispersion is a rather rare effect which appear in very particular situations. Nevertheless, they are very interesting from many points of view. So, can we get something with dispersion from the Jordan chain? Yeah. Okay. Okay, the first equation of Jordan n-dimensional Jordan chain. Let's impose the following constraint with the second order derivative now, where u n plus I is Laplacian, you end up with the following system of equations. It's n-dimensional. Of course, the dispersion law is pretty strange somehow in this case, but okay, probably describes something interesting. I don't know. But anyway, in the case n equal 1 is just KdV equation, as we expect. And if you consider another reduction, where u2, u3 up to un equal to 0, so u1 only remain, we end up with the following equation, where Laplacian is full n-dimensional Laplacian. So it's not a one-dimensional equation. And what type of equation we have? Okay, it's a good question. But anyway, it describes effect of dispersion, or probably also diffraction, the combination of that. Okay, we can extend this example to more complicated choice, where alpha, I, k, l are arbitrary constant, and we'll end up with the following system equation, which contains third-order derivatives. And finally, let's consider the following constraint. And the second-order derivatives, u n plus I is Laplacian I ui, where Laplacian I is full Laplacian minus term with derivative respect to xi. Why is it of interest? Because in this case, our first equation of Jordan chain is reduced to the following equation. Can you describe the effect of diffractions? In particular, if we impose the following constraint of function u, we end up with a single equation for u1, and this equation has been considered 10 years ago by Boris and T, and it exactly described sort of n-dimensional extension of Kp, which is the effect of dispersions. Okay, if you will choose n equal to 2, you end up with a Kp equation, we have a known Kp equation. So, continue with it. In these examples, we see the Jordan chain contains also many examples with third-order derivatives of different types, with different behavior, and so on and so forth.
Sorry, Boris, this is dispersion is Kp.
Sorry?
It is dispersionless in the n equal to 2 case.
Why? No. No, this is just a second derivative.
In which variable?
Sorry? No, it should be delta E is you see sum over derivatives except I. So take Laplacian and subtract the second order with respect to xi. Okay? So in this case, n equal to it will be just derivative with respect to y or x2. This one. No, this is exactly.
Yeah. So what is the
Oh, no.
where is the dispersive?
I forgot the sort of derivatives. Okay, I'm sorry.
Okay.
It was too fast. Yes, of course. No, it's dispersive, you are right, but you can add sort of derivatives easily. You can continue this is very good observation. Thank you. It was written just where I was here, just to connect my talk somehow with something dispersion. Unfortunately, this example is new. Okay. Well, then you can continue combining all the and proceed. And there are a number of questions you can ask. And I cannot answer almost all these questions, but nevertheless, probably from my point of view, this is not completely trivial and may have some implications, different things. There are possible extensions. In fact, I spoke here about only simple Jordan block with one eigenvalue, one Jordan block. One can extend it to general case. In fact, there are already papers devoted to study of this subject. For instance, recent paper of Lindling and Ferraponto about connection of the quasi-linear system with Jordan block with a modified KP hierarchy. So behind all this constructed Jordan blocks, there are many interesting unknown things. Or one can extend the Jordan chain to the following one, where instead of UK will have arbitrary functions, you will get other type of equation. And so many equations remain. There is much space to do something. With the hope it will help to understand something in physics, but also in mathematics. Okay, thank you for your attention and your patience.
Great timing. And any questions?
So trivial.
Yeah, I would like to ask one, because you mentioned it.
I'm sorry.
The Hamiltonian formalism.
Dispersion. I'm not right for some class. Of course, no, as I mentioned for the in fact good question, in n-dimensional case, Novikov, Dubrovin, and Mock analyze the Hamiltonian structure of corresponding equations. And for sure, the approach can be applied to that. What will results? I don't know. Probably something special. I don't know.
Actually, I've got a question. So when you write the Jordan block equation and you connect it to the, say, the Burgers equation by setting U2 equal to 1 second derivative of 1. So if you want to solve the initial value problem for the Burgers equation, you need to impose a mixed initial boundary value problem of the Jordan.
Yes, of course. Unfortunately, if you pass to in one dimension to build this, to complement this scheme, you will not have possibility to formulate the full initial value problem because of the several constraints. For some equation is just dictated by equation. For some, not. I cannot. If you go to a higher dimension, situation becomes much more complicated. I can say this is a very good question. What is going on with the initial?
Questions, let's thank the speaker again. So tomorrow at 11 in this room. So we'll talk about macros. And now, as you know, it's a tradition. We have a drinks and reception in the first floor in the main building. So we just need a bit of faucet.
I think this it's confusing. It's just
Yeah.
but it's also no, it's like saying
Solution, Jordan.
yeah, you kept saying solution of the here, so put it here. Solution. So obviously.
No, solution, Jordan.